This is quadratics with complex numbers as solutions. Let's start with a review of how to simplify radicals. The square root of 108. Well, we'll start by factoring 108. And we're looking for the pair of factors that has the largest perfect square. It turns out that is 36. So we're going to use 3 and 36 as our factors under the radical. Our next step is to separate those two radicals. The square root of 36 times the square root of 3. The square root of 36 is 6. But the square root of 3 cannot be simplified any further. And so our answer is 6 times the square root of 3. Let's take a look at another example. If we were to simplify the square root of 24, then we would start the same way and factor 24. The largest perfect square is 4, and so we're going to use the factors 4 and 6 under the square root. We're going to separate those two factors, simplify the square root of 4 to 2, and so our answer is 2 times the square root of 6. Pause now and copy both examples on this slide. Now, what does it look like if we're actually solving using the quadratic formula? Well, we have this quadratic expression here. We're going to start by identifying A, B, and C. And then we're going to plug those into the quadratic formula. We have negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Now we're going to simplify this expression, and when we do, we end up with 18 plus or minus the square root of 260 divided by 2. Now let's focus in on the square root of 260 for a moment. We're going to factor that. And when we do, we're going to find that the largest perfect square is 4. And so we write that as 4 times 65. Then we're going to separate the two radicals and simplify even further. We know that the square root of 4 is 2, so we end up with 18 plus or minus 2 times the square root of 65. The square root of 65 is as far as we can go with simplification without making it a decimal, and we do not want to make this a decimal. That whole thing is divided by 2. Now I'm going to break that up into two fractions. Now 18 divided by 2 is 9, and 2 divided by 2 is 1, and we treat the square root as if it were the same as a variable, and we leave it there. Now pause now and copy this example. Let's look at another example. We have this quadratic expression. We again begin by identifying A, B, and C. Then we plug the appropriate values into the quadratic formula. Simplify. We end up with 8 plus or minus the square root of 160 divided by 2. So we're going to look at the factors of 160 for the one with the largest perfect square, and it turns out that is 16. 16 times 10 to be exact. So we're going to break up those two radicals and end up with 8 plus or minus the square root of 16, which you know is 4, times the square root of 10, all divided by 2, and we simplify once more the square root of 16 into 4, and we end up with 8 plus or minus 4 times the square root of 10 over 2. Now I'm going to divide 8 by 2, and I get 4, and 4 by 2, and I get 2, and I leave the square root of 10 as it is. Pause now and copy this example. Now, exactly what are complex numbers? They are numbers that have imaginary numbers, they include imaginary numbers, and they're used to describe solutions of quadratics that have no x-intercepts. Now pause now and sketch this graph and write down this definition of complex numbers. Now, what are imaginary numbers? Well, the square root of negative 1 is known as an imaginary number, and the notation we use is this lowercase I. The square root of negative 1 squared, or I squared, is negative 1. Now let's look at an example of how this is used. Suppose we have the square root of negative 2. Well, we're going to factor out the negative 1. Then we're going to break up those two radicals. Then we're going to represent the square root of -1 as an I. Now, when we're writing imaginary numbers, we never leave the I behind the square root. We always move it to the front of the square root. And so I'm going to do that now. And the simplified version of the square root of -2 is I times the square root of 2. Let's look at another example, the square root of -4. Now the first thing I'm going to do is factor out -1, and then I'm going to separate those two radicals. Then I'm going to take the square root of 4. That is 2. And the square root of -1, as we have discussed, is I. And so my answer is 2I. Pause now and write down this example, both of these examples, in your notes. Now let's take a look at another example. 5 times the square root of -121. Well, we're going to start, as always, by factoring out the -1, breaking up the radicals. Now we're going to look at the square root of 121. It turns out that's 11. And then 5 times 11 is 55. And this I, square root of -1, is I, so our answer is 55I. And our last example is negative square root of -96. Well, we start the exact same way. We factor out -1, and then we take a look at the factors of 96. Turns out that the largest perfect square in 96 is 16, so we're going to factor that out and separate that out and end up with negative square root of 16 times the square root of 6 times the square root of -1. Now the square root of 16 is 4. The square root of 6 cannot be simplified any further, and of course we represent the square root of -1 as an I. But remember, I said that we never have the I behind a square root. We always move it in front. And so we're going to do that now. And our answer is -4I times the square root of 6. Please pause now and copy these examples. Now, we're going to transition now to solving quadratics that have imaginary solutions. So let's take a look at this quadratic. Well, we're going to use a quadratic formula, so we have to identify A, B, and C, and then plug those numbers into the quadratic formula and simplify. When we do, we end up with -10 plus or minus the square root of -4, all divided by 2. Now I'm going to focus in on the square root of -4 for a moment. I'm going to factor out the -1, then break up those two radicals, and then simplify. The square root of -4 is 2. Last but not least, I'm going to divide -10 by 2, and that gives me -5. And I'm going to divide 2 by 2, and that gives me 1. And I leave the I as is. I treat that like I would treat a variable. So my answer is -5 plus or minus I. Please pause and write down this example. Here's another example. As always, we start by identifying A, B, and C. Then we're going to plug those into the quadratic formula, simplify the three parts, -b, what's under the radical, and the denominator, and we end up with -4 plus or minus the square root of -48 divided by 2. I'm going to simplify that square root of -48 by factoring -48 and looking for the largest perfect square and factoring out the -1. And then I'm going to break that up into 3 radicals and simplify the square root of 16, which is 4. I can't simplify the square root of 3 anymore, and I'm going to simplify the square root of -1 to be an I and move that in front of the radical. Next, I'm going to divide -4 by 2. That gives me -2. And positive 4i square root of 3 times by 2, and that gives me 2i square root of 3. Pause now and write down this example. Now let's talk a little bit about complex numbers. What are they and what do they look like? Well, they're in this format where A is the real number, like 1, 2, 2 million, and BI is the imaginary part. Pause now and write this down in your notes. Now, when you're adding complex numbers, you add the real parts together and you add the imaginary parts together. So I'm going to add 3 and 8 and get 11. And I'm going to add 7i and 11i and get 18i. Pause now and write down these instructions and this example. When I'm subtracting complex numbers, it's very similar to addition, only now I have to distribute the subtraction sign and then add like parts. And when I distribute that subtraction sign, I get negative 15 plus 2i. And now I'm going to add the reals to the reals and get negative 10, and the imaginaries to the imaginaries and get plus 12i. Please pause now. Write down these instructions and this example. When I am multiplying complex numbers, I use FOIL. Remember that I squared is equal to negative 1, so I can simplify that. I end up with 15 minus 19i plus 56, which simplifies to 71 minus 19i. Please pause now and write down this example in your notes. Now, when I divide complex numbers, I have to multiply both the numerator and the denominator by something called the complex conjugate of the complex number in the denominator. Now, here's what the complex conjugate looks like. Here's an example. If I have 3 minus 5i in the denominator, then the complex conjugate is 3 plus 5i. It's not too hard. You just change the sign of the addition or subtraction operation. Now, here's an example of how this would work. But first, please write down these instructions and this example of a complex conjugate. Now, here's an example of how you would do this. You notice I'm multiplying both the numerator and the denominator by 3 plus 5i. This is the complex conjugate. So I'm going to have to FOIL the numerator and then FOIL the denominator. And when I do, I get these long expressions, which I am going to simplify to be 21 plus 41i minus 10 all over 9 plus 25, which is 31. 34. Now, you have to do this because it is mathematically illegal to have I in the denominator. So you're going to want to take care of this and make sure that you write down this example and understand how to do this. Pause now and make sure that you have this entire example in your notes. Now, I'd like you to take a few minutes and try these, and here are the answers in red. Please make sure that you note any questions you have and bring them to class. I'll see you then.